Hi there. Thanks for joining us on a Q&A edition of Space Nuts. Andrew Dunkley here, your host. Great to have your company. In this episode, we are going to talk about a universe without black holes, dark matter, or dark energy. What would it be like? Yeah, probably completely different. Mightn't exist at all. Don't know. We've also got a question about loss of energy and the age of the universe. Another universe question, the early universe and all the matter and the stars and things, and why we get so surprised when we discover something that's old, because it's all been there from the very beginning. It's a good question. And Titan's atmosphere has come up from one of our audience members. So we'll answer all of those questions today on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back again for more. Can't believe it. It's Professor Fred Watson, astronomer at large. Hello, Fred.
Well, I can't believe it either. How are you doing, Andrew?
Well. Yeah, thank you. You're looking well too. In fact, I would go as far as saying that since you left the public service, you seem a lot less tense, a lot happier.
It's really interesting because I don't have to scan my government laptop every morning to see what meetings I've got during the day, and that makes the day a lot more relaxed. I do still have meetings, but they're under a lot better control.
Yeah. Oh, that's good. Shall we tackle some questions?
Well, let's attempt it. Let's see.
All right. Let's go to our first one that comes from Reynold, or he may pronounce it Renault. How would our universe behave without black holes, dark matter, and dark energy? At what phase did dark matter and dark energy appear? That's a double bunger. What do you think, Fred?
Yeah, I think it's a profound question. And, it's at the forefront of modern day cosmology. So we think that it was the dark matter that really caused the ability of the universe to form galaxies, stars and galaxies, because what we think happened was that the dark matter came first and sort of coalesced into what we call the cosmic web, this kind of honeycomb structure of sheets of dark matter, which attracted the hydrogen that at that stage pervaded the universe to form a similar structure, because the hydrogen collapsed gravitationally to sort of mimic the underlying dark matter structure. And then, during that collapse, many stars were formed. Star formation took place. Galaxies formed because the stars, they all formed in these large blobs of matter. And we see that today. We still see, when you look at the structure of where galaxies lie in today's universe, you find that they make up this honeycomb, which basically mimics what we see in the cosmic microwave background radiation, which we think is the precursor of those galaxies. That's the sound waves going through the early universe. So we think that without dark matter, the universe will be very different and wouldn't have this underlying web, and maybe galaxies and stars wouldn't have formed. That's really interesting. So now dark energy. Go ahead.
No, I was going to say, so if dark energy was the driving force and it didn't exist, would our universe have formed at all anyway?
Well, yeah, dark energy is a different thing. It's the
dark matter. Sorry.
Yeah. So with that, yes, dark matter we think is what allowed galaxies to form. The universe itself might have formed. We don't really understand the Big Bang well enough to know just where it all came from, but we might have had a universe devoid of dark matter, just full of cold hydrogen and not really doing anything. So that's pretty boring to the universe. And dark energy really is a property of the expansion of the universe. So it's telling us that space itself has energy. So I think the second part of Reynolds' question is, at what phase did dark matter and dark energy appear? So we think dark matter appeared right at the beginning. Now, dark energy was probably always there. This is a hot topic in cosmology, but we think it's only manifested itself in the last 5 or 6 billion years. In other words, about half the age of the universe. And we think that's probably because dark energy might have been there all the time, but it didn't have enough energy to cause the universe's expansion to accelerate, which is how we see dark energy. It didn't have enough energy early on because the galaxies and stars, well, the galaxies themselves were too close together, and their mutual gravitational pull was enough to sort of slow down the dark energy and hide its effect. So we think dark energy might always have been there. The big question is, has it evolved? Because for about the last 20 years, the thinking has been that it's a constant, that it's a property of, the same amount of dark energy per unit volume of space, per cubic centimeter, if you like, of space. So it's said that, in other words, the dark energy is proportional to the volume of space. So as the space expands with the expansion of the universe, you get more dark energy. But the thinking now is that maybe that's not quite true. There might be a slight evolution effect over time, which is still being explored.
So, another piece of his question was, a universe devoid of black holes. What would that be like?
We think black holes are a natural consequence of the formation of stars and galaxies. Without a universe without black holes might not be that different, because until 40 or 50 years ago, we thought the universe didn't have black holes.
Yeah, that's true.
And it's only by a lot of fairly detailed and careful research that we've discovered that there are black holes everywhere. So yes, it's an interesting question. I don't know that the consequences, there would be a lot less high energy events going on in the universe. We wouldn't see quasars for a start. Quasars are powered by black holes. They're delinquent galaxies with a black hole at their center.
Okay. But if you didn't have any of that, any of the black or dark stuff, you might just have a universe that's full of hydrogen looking pretty boring. I suppose there might be the odd reactionary event that would create something, but yeah, it wouldn't be much to look at. It would be Boresville.
Yes. Well, it would be Boresville, because without the formation of stars and galaxies, well, in particular stars, without the formation of stars, you don't get the heavy elements. All you get is a universe with hydrogen, helium, a little bit of lithium, and a couple of other things, and that's it. So it would be a very boring place. And talking of that, that is one of the main targets of the square kilometre array, because cold hydrogen actually radiates in relatively low frequency radio waves. And the square kilometre array is going to be able to look so far into space, in other words, so far back in time, that it can see the dark ages when the first stars had not yet come into being. And all there was cold hydrogen. So they'll be able to map that cold hydrogen and see whether it does actually fall on the cosmic web as we believe it did.
Fascinating. Reynold, the answer to your question was there'd be a very different universe without any of that stuff, probably pretty boring. And it was probably always there at the beginning, dark matter and dark energy perhaps as well. So, yeah, it's a great question. Thanks for sending it in. Our next question, Fred, comes from one of our regular, although we haven't heard from him in a while, sender-inners, Buddy.
Hello, Space. That's his buddy from Oregon again. Hey, how much of the energy of the universe is kind of like gone, basically? Is never going to touch anything, or is going to just continue forever, like light or gravitational waves? Plus, maybe the potential of the energy of moving objects. How much of the universe's energy is tied up that way, guy? I got one more question. Is it possible to calculate the age of the universe from the half-life of uranium or lithium? All right, guys, keep up the good work. Love the podcast.
Thank you, buddy. That's two very, very good questions. So we'll tackle them one at a time. He was asking about energy that's been lost in the universe. I assume he means over the time the universe has existed. That there was a big bang, everything expanded very quickly, and then it slowed down. Now it's speeding up. There's a lot been happening over billions and billions of years, but is there energy loss in that process?
Great question. One that I'm thinking aloud here, Andrew. So the energy budget of the universe is really interesting because it sort of ties in with the mass of the universe as well. You know, mass, as we know, has an intrinsic energy. Buddy is talking about the kinetic energy of moving objects, and that's certainly an energy component, but I think it is vanishingly small compared with the equivalent of the mass of the universe when you convert it to energy with E equals mc squared. So most of the energy of the universe is tied up. So most of the energy of the universe. I'm getting myself in a knot here. If you regard mass as part of the mass energy budget of the universe, and you draw a pie chart, the stuff we can see is about 5% of that energy budget. So that's all the mass equivalent, the energy equivalent of all the mass in the universe. And it's very, very small compared with dark matter, which is about 5 times bigger. And then the rest, which is 75 or 80, about 75%, is dark energy. So dark energy is by far the biggest energy content of the universe, and the rest almost doesn't matter. It is an incredible situation that we have, that the biggest energy component of the universe is something we actually don't understand. It's making the universe expand ever more rapidly. Really very, very interesting. Just moving on to uranium. Uranium's not something that you can use to determine the age of the universe, because it was created in supernova explosions, which occurred after the universe was formed. We think heavy elements like uranium are created within massive star, either collisions, neutron star collisions, or massive supernova eruptions. You can use uranium. Obviously, it has a half-life, and you can. I think that might be one of the ways that you determine the age of the Earth. Actually, when I think about it, 4.6 billion years. I think the age of the Earth is partly due to our understanding of the radioactive decay of isotopes like uranium. So yes, it's got a place in cosmology, but not in regard to the Big Bang itself.
Okay. You also mentioned lithium, same deal.
I did, yeah. Now, lithium's not that's what I was just looking up. I'm not aware of the radioactive properties of lithium. Let me put it that way.
Okay. Yeah. Well, we know about its properties when it comes to energy use on Earth, and it's a dwindling resource, so they've got to find something else eventually. And I think they're working on sodium batteries. And there's plenty of that stuff around. But so if you can't use the half-life of uranium or lithium to calculate the age of the universe, what do you use?
The first way it was worked out was simply by measuring the Hubble constant, which is the rate at which the universe is expanding. If you invert the Hubble constant, you get the time, how long it's been expanding for. You can basically use that simple number to work out when everything was all together in one place. But that assumes that the expansion has been uniform throughout, and we don't believe that's the case now. So you've got to modify it. So these days it's a combination of looking at the distribution of galaxies in the universe, plus our observations of the flash of the Big Bang, which we can still see, of course, as a cosmic microwave background radiation. And you can deduce from that how old the universe is, because you know it was visible light when it left and it's now microwaves, and that's a simple calculation as well.
Yeah, I suppose in terms of dwindling energy or lost energy in the universe, you can look at, I think we've spoken about it before, you can look at photons, which do die, especially if they hit something, but that energy transfers into something else, does it not?
That's correct, yeah. So it's conserved. That's right.
There you go. Okay. Thank you, buddy. Great to hear from you. It's been a while. Hope you're well. Our next question comes from, hang on a sec. We've got to do this first.
0G, and I feel fine.
Space nuts.
There we go. Always got to chuck one of those in. Ben has sent us a question, and Ben asks, in the early universe, it was physically much smaller, but the total amount of matter/energy was the same. So everything was much closer together than now. So wouldn't that make it much easier to build stars, galaxies, and stuff, even supermassive black holes? Yet we are supposed to be surprised that these structures existed in the very early days. Why so? I would be surprised if huge compact structures didn't form quickly, as the ingredients were so readily available. Ben Harding. Thank you, Ben. We've kind of been talking about that stuff as a part of today's program. And yes, you bring up an interesting point. We get excited when we find a primordial black hole or an ancient galaxy that seems to, almost be as old as the universe itself. Which has happened in recent times. Should we be surprised, Fred, or is Ben onto something? Look, it was all there in the first place. Why are we getting, super, super excited about it?
So if our models of galaxy formation were perfect and a perfect representation of reality, then we wouldn't be surprised because the models will predict that. But the models need fine-tuning. So those surprises are, I think, to be honest, they're often beat up by the media, including space nuts. There is an element of, researchers who are the ones who put together models of the way galaxies form and evolve. They're the ones who've, in some ways, had to rewrite their models. They've had to tune the parameters. We had a talk at the 50th anniversary of the Anglo-Australian Telescope, that symposium that I was chairing as the local organising committee chair, science organising committee chair, not very long ago. One of the talks was about exactly this. And that particular speaker said, we shouldn't be surprised that these structures formed so early in the universe, because the ingredients were there, exactly as Ben says. But there's a bit more to it than that. You've got to have the gravitational pull that's provided by that cosmic web structure that we were talking about a few minutes ago. That needs to be in place as well. And that must have formed very, very early on in the history of the universe. That's what we'll learn from the square kilometre array. We might get surprises from the square kilometre array as well, because we think there's at least a time of more than 100 million years when the universe went through the dark ages. There were no stars shining. Now that might turn out to be an underestimate or an overestimate, and it might surprise the theorists when we start to get the results from the square kilometre array, which won't be too far down the track, I don't think. Maybe 2 or 3
I was
years.
about to ask you that. It can't be too long before they switch that on, but
it is still a while. Yeah, it's 2028 or thereabouts.
Yeah, all right.
But they will switch on bits of it beforehand, so we might glean stuff. It is an array, so it's not just a single telescope.
Yes.
Yeah. Large
Very good. Thank you, Ben. I think we basically answered it. That yes, because of modelling and it's not an exact science, these discoveries are quite surprising from time to time. And not all the stuff was there in the first place, I suppose, Fred, because the consequence of the Big Bang and that mix of materials that created more materials and new discoveries being made as a consequence of that, I suppose.
Yeah. So, I mean, the modelling of the Big Bang's fairly pretty well sewn up. And it's within the first few minutes that you actually get atoms forming, but they are hydrogen and helium. And then you've got to wait a long time, probably 100 million years, before you started getting carbon and oxygen and the other things that are formed by the interior of stars. And that, that's a fairly coherent picture, which, as I said, will be demonstrated, we hope, by the square kilometre array. What will be a surprise there is if they, when they analyse the signal coming from that early gas, if heavy elements were present in that early primordial gas, then we really have to start rewriting the textbooks, because at the moment we don't think there were any. So there's a challenge for the square kilometre array, and that would probably win a Nobel Prize, a discovery like that.
Yeah, I imagine so. So Ben's basically asked his question a few years too early.
Yes, that's right. So if a Nobel Prize came from that, it would please me enormously, because I'm on record in Hansard as having promised the government that the square kilometre array would win a Nobel Prize.
Okay. Yeah.
That was a few years ago.
Well,
that was, yeah.
I'm just going to write a note because we're going to follow that up. Okay, thanks, Ben.
Okay, we checked all 4 systems and keying was a go.
Space Nuts.
And our final question today comes from Jens.
Hello, Space Nuts. This is Jens from the forest of Dalsland in Sweden. As we all know, Saturn's moon Titan is a very special place. So here is my question. How did Titan become so special? How did it accumulate its thick nitrogen atmosphere and all its methane and ethane? There are dozens of moons of the outer planets, but only Titan has an atmosphere. What is it about Titan that made it become different from all the other moons? And another related question. It is often said that Mars is too small to retain an atmosphere in the long term. But Titan is even smaller. How come Titan can retain an atmosphere when Mars cannot? Thanks for a great show.
Thank you, Jens. Great to hear from somebody in Sweden. And, gee, they were great questions. Especially that last part, comparing Mars, that couldn't hold an atmosphere, to Titan that's smaller, that can hold an atmosphere. And how did Titan get its atmosphere in the first place? Because it's unique. I think that was a reasonably good paraphrasing of it.
It paraphrases it very well, yeah. And I can paraphrase the answer, which is basically, I don't know.
Homework time.
Yeah, I think we will do some homework on this, but it's a great question, Jens. And I, just thinking about it, with Mars, the obvious difference between Mars and Titan is that Mars is bigger than Titan, but Mars is much closer to the sun. And so, while it's not in the Goldilocks zone, it's near enough to the sun that we think the sun's radiation, and by that I mean the subatomic particles, has helped to strip off the atmosphere from Mars, which is, some of it is water vapor that's frozen out, a lot of that, but a lot of it was dissociated into, the water was certainly dissociated into hydrogen and oxygen, and the hydrogen's just gone into space. Likewise, probably some of the carbon dioxide. I think there's a temperature difference there. But once you get to Jupiter, now Ganymede is bigger than Titan. And Ganymede doesn't have a skerrick of an atmosphere. There's nothing there at all. So it's a really interesting question why Titan should have that thick atmosphere. And I'm not an expert on planetary science, but I will take that one on notice because I think that's worth following up just to find out. It's such a great question, and it's it's glaringly obvious. Why is this body in the outer solar system? Why is it clung on to an atmosphere that is thick and murky when we've got a similar sized object, Ganymede, not that far nearer to the inner solar system, in orbit around Jupiter, that doesn't have any sign of an atmosphere like that. So that is one I'll come back to, and thank you for the question.
Okay. Just throwing it out there. Could it be something to do with the volatility of Titan? It's volcanic, is it not? And it's throwing up a lot of these nasty, smelly gases. And could it constantly be renewing its atmosphere, which Ganymede cannot, perhaps?
These are the cryovolcanoes. We think it's a mixture of water and ammonia that comes up from them, and not what the kind of thing that we imagine when we think of a terrestrial volcano. So the volcanoes are coming up from the ocean layer beneath the ice of Titan, because Titan's surface is solid ice, as we believe is Ganymede's. So it's such a contrast. I mean, in a sense, my first thought about this was, well, gas giants are, they grow their gassiness because they've got a massive core that's been built up by the fact that they're beyond the ice line. So ice has formed, and they've probably got an icy core. And whether you can apply the same argument to Titan, I'm not sure. I need to check on that. So thanks for the question, and we'll have a look at it. I'm going to put an asterisk next to my notes.
We'll put a pin in that one and try and come back to it in a later episode. But great question, Jens. Very, very good. And I hope all is well in Sweden, although you're heading into the colder months. So I won't be visiting for a while.
Well, we will. We'll be there not next month, but the month after. We'll be in Sweden.
Oh, wonderful.
In the Far East for our Arctic tour, yeah.
Excellent. Okay, that's it for today. Thanks to everyone who sent in questions. Don't forget you can send us questions as well via our website, spacenuts.io. Just click on the AMA link up the top and send us your questions through that. And have a look around while you're there, particularly the Space Nuts shop or the Space Nuts supporter button if you want to push that. What it does is as soon as you push that button, it sends out a Trojan and empties your bank account. No, it doesn't. No, it doesn't.
Don't even joke about that.
No, shouldn't really. Good grief. No, it doesn't. It's purely voluntary. Thanks, Fred, as always. Great to chat, and great questions again this week.
Well, they're terrific questions. Yeah. Thank you very much, everybody. And thanks, Andrew.
No worries. Catch you soon. Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio for telling me about the Trojan horse problem we've been having. No, I'm kidding again. No, he didn't, although he's working on it. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. See you then. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.